So what do we have right now? We know that the physical layer gives us a sequence of ones and zeros. For example, this. What else? Due to framing, we know, okay, maybe this is the start of a frame and somewhere here is the end of a frame, just an example. We know maybe there were errors or everything was okay, so we can decide this. Maybe we can even correct something. So the third function in the link layer, flow control, because now it may happen that a sender is simply flooding a receiver. Okay, so let's start with a very simple scenario. So let's assume that network layer, so layer 3, says, okay, please send, so the higher layer, please send a long stream of data packets from A to B. So what do we do right now in the link layer? How do we handle this stream of data packets? So for example, a video stream or a large file. What happens? Again, an insight from the programming point of view. So what kind of data types do we have? How do we define, for example, in a programming language, a packet? So you see here the examples, the type definitions. So that's an interface with the layers 1 and layer 3, as I will show on the next slides. So you can define a packet, a type of a packet. We will learn what a sequence number is for, and acknowledgement, and some data fields, etc. So that's just something to look up. We need some functions. So what type of functions? For example, we have to wait for events. Events are quite important. We'll learn how we use timers. We have data that goes to the network layer, coming from the network layer, so from layer 3. The same is true for layer 1. Timers, events, packets coming in, we have to react upon them. So many different functions. Okay, and so in the end, if we look at the link layer from a programming point of view, we see that, okay, we have data coming from the network layer, data we send to the network layer, to physical layer, from physical layer, and we have certain functions to enable the layers. We have functions to start timers, to stop timers, to start special timers for acknowledgements, and we'll see where we need those. Just an example, if I send a packet and I wait for an answer from the other side, so how do I wait? Well, I start a timer, then I have a timeout, and if I do not get the answer before there's a timeout, maybe I know something went wrong. So we'll come back to this. Okay, so we have certain functions, and now we start with a very, very simple mechanism. A very naive approach on how we can send data from A to B. And remember, the scenario was as follows. So a stream of data. So from the network layer, from the higher layer, layer 3, we get some data. And then we, as a very simple link layer, simply say, okay, we forward the data to our link layer. So to the physical layer from the link layer. So network layer to physical layer, and the link layer is basically forwarding function, very simple. So we start with a simple example, and we indicate this here. So if it goes to here, our physical layer, then we send the data from A to B. So transmission here in this example is only in one direction. Simple example. We do not number the packets. We have no acknowledgements. We ignore the processing time. So it's very simple. We have the procedure sending something, receiving something. That's an infinite loop, as you see here on the left side. So we fetch some data from network layer and we give it to the physical layer. Fetch data and give it to the physical layer, and then we send it over. On the receiver side, we start waiting for an event, we wait that something happens, and then suddenly data shows up at the physical layer, and we as a very simple link layer, also on the side of this computer B, we simply give it then to the network layer. So from layer 1, we give it to layer 3, and then we wait again until something, oh, the next data, okay, there's some data, physical layer, we give it to the network layer, and we wait again, and so on. And we could run this in an infinite loop. We fetch the data, we send the data, on the receiver side, we get the data, and we pass it to the network layer. So this is very simple. So basically, this is all you have to do. Is it? So network layer gives you something, and then you forward it to the physical layer, and that's it. Okay, but yes, it's very simple. The problem is we have too many, or we made too many assumptions that simply do not help. So we assume the channel never damages frames, never loses frames. So, but what happens if we flip a bit? That means we have an error. We now learned that we can detect errors using a CRC, frame check sequence, and that means we have to drop the packet. What happens in our simple scenario? Well, the sender A simply sends data all the time, assuming receiver B simply fetches the received data from the physical layer, consumes it, forwards it to the higher layer. But what happens in case of an error? So we cannot handle it. Also, if we simply lose a frame somewhere, this could happen. We also assume that the higher layer on side of B is always ready to receive something. Because we learned, okay, as soon as data comes in, we simply forward the data to the higher layer. But what happens if this is not the case? So we make the scenario a bit more complex. So again, the network layer on the sender side here asks to send a long stream of data from A to B. Link layer, now still the simple one, but what happens if here the network layer at computer B is not always ready? That means maybe I cannot consume the data. So data comes in our simple example, we directly forward the incoming data from phi to the network layer. So layer 1 to layer 3. So that was the simple job of layer 2, this forwarding. But what happens if layer 3 says, sorry, I cannot handle more data? So then we have to start, well, doing something. Or maybe we could buffer. So that symbolizes a queue. So we put the data into a queue until the network layer is ready to receive something. Okay. This helps for some intermediate, some stop for a very short time, so that the network layer says after a short period of time, okay, now I can consume the data again. But what happens if the network layer simply is too slow? So what happens if you have on the left-hand side your huge systems, your compute center, your cloud, and on the right-hand side you have your poor small IoT device? So you will flood B, but B cannot consume data fast enough. And this is exactly where we need flow control. So we need mechanisms that control the flow of data to prevent receiver overflow. There are many reasons why a receiver says, okay, right now I cannot receive anything. Maybe there are other processes running. So the process receiving data forwarding is one maybe out of many processes. There are other processes running on a computer and whatever the computer does. So maybe the computer is simply busy. Okay, this could be the case. Or the hardware, the processor is simply too weak, cannot process data fast enough. So big fast computers produce maybe 1 gigabit per second. This cannot be handled by all, let's say, weaker computers. Okay, so one job is controlling the flow of data. How can we do this? There are 2 types of flow control. Type 1 is a flow control using feedback. So what does it mean? That's a classical situation if you have a teacher and school kids, and if the teacher, as always, talks too fast, the kids could say, please slow down, stop. So the kids give a feedback. Also, students can tell the professor, please slow down. Too much information per second. So slow down. So the receiver sent back information to the sender, and in a very strict case, the receivers could give permissions to the sender to send more data. So the students could say, dear professor, now you may talk again. Stop. That was already too much. I have to think. After thinking, now you may talk again. So that sounds good. That works. But for our technical system, we need bidirectional channels. So otherwise, the feedback will never get back. Think of broadcasting of news. So maybe you're still thinking about the news you heard. You cannot say stop. There is no feedback channel, so the news program will continue. But on the phone, there's a feedback. If someone talks to you, you can tell them, oh, wait a second, I have to think about it. So this is our feedback. So we send back information. Channel has to be bidirectional. For unidirectional channels, that simply does not work. So we need the reverse direction for the feedback to get to the sender. So that's one way of doing it. There's a second way of doing it, and this is called a rate-based flow control. So we could also have a certain protocol that limits the data rate without any feedback. So, for example, we can agree via a protocol that the maximum data rate is 10 bytes per second. Okay? And then that means you limit the rate. There are many more, let's say, versions and variants of this rate-based flow control, how this can be performed, etc. Here, we focus mainly on feedback-based flow control. So we need a feedback. The receiver will tell us something about how much data the receiver can consume or can at least buffer before it consumes the data. So consuming always means that the higher layers can do something with the data, can process it, can hand it over to an application. That's meant by consuming the data. Okay, how does this work? Again, we start with a very simple approach. And basically the simplest approach, the simplest protocol we can think of is called a stop and wait protocol. So we need the bidirectional channel because we have to be able to say stop, that's enough. And the idea here is that the sender sends a piece of data and then waits until you get an okay, what we call an acknowledgement, or ACK for short. We get an ACK from the receiver, or, and now you see why we need those timers, we reach a timeout. Why a timeout? Think of you talk to someone and you say something and the other side simply does not react. After a while, and this is your internal timeout, you will maybe repeat your question until the other side answers or tells you at least, yeah, got it, okay, I have to think. But either you get an acknowledgement within a certain time period or you have to do something. So that's the idea. Okay? So, and as I said, if the data is not acknowledged, then maybe you repeat it. And if it's acknowledged, then you go on with the next piece of data. So how does it look like? Now again, our A and B. we send a certain frame, layer 2, B consumes it, and if everything is fine, you send back the acknowledgement. As soon as we get the acknowledgement, we can send the next frame. Get an acknowledgement, send a frame, get an acknowledgement. Okay, that looks nice, but there are several drawbacks. So you see here, if everything works perfectly, yes, nice, but why not sending all the data at once? This requires maybe a buffer. Okay, we'll talk about this. There could be but there could be something else. What happens if we lose a packet? Okay, there's this timeout, so we have to resend it. What happens if we lose the acknowledgement? Can we distinguish between losing the data packet and losing the acknowledgement? We'll come back to this. But for now, remember, we have a very simple protocol, stop and wait, where you send data, you wait for the acknowledgement, you send the next data, wait for the acknowledgement. Not very efficient. You have to wait all the time for the acknowledgement. And we have the open issue with errors. So talking about errors, now we drop the assumption that the channel is error-free. So it could be the case that we lose a packet between A and B. Losing a packet, this could be a flip bit, and then the checksum will tell us there was an error. If there's an error in a packet, a frame here, we drop it. So we will not forward to higher layers packets with errors. Typically we don't do this. So, okay, let's drop this assumption. And if the channel is not error-free, so the frames and the acknowledgements, both, they could be damaged, they could be lost, flipped bit, etc. If we have this situation, we have to do a bit more. We cannot simply say, okay, we repeat it. The problem is what to repeat. Let me explain this. Look at the scenario on the right-hand side. We send a packet from A to B. These are our computers, here A and B. And indicated in red is the frame and blue is the acknowledgement. So, and as we'll see, we will number these packets. Well, now we sent them. Now it could be the case that we send a certain packet and there's an error. So what happens? After a while, we have to resend. So we need timers for each packet we send. We start a timer. Same here, we start a timer. But there's the acknowledgement, fine, so I don't have to resend anything. But if we do not get the acknowledgement in time, we have to resend the packet. And then we get the acknowledgement. And then we can continue with the next packet, etc. So, we pass it to the network layer as usual. So now, coming back to this M and the 0 and this alternating bit, etc., what does it mean? Well, the point is, we have to give the packets a number. In the simplest case, a single bit is sufficient. Why? Let's assume we start with the bit 0, so that's the packet number 0. And then the next could be packet number 1. Okay, so now B never sees this error. That's, by the way, something important. If we look in these time sequence, these message sequence charts, we as humans, we see, there was an error. Now, bring yourself in the situation of the receiver B. B, for example, will never see that there was an error. B will simply think, okay, A doesn't send anything to me. Okay, nothing, we won't receive anything. It might be the case that B receives a packet, a frame with an error, with a flipped bit, but then it drops it. So that's equal to I don't get anything. Or the physical layer may drop the packet in between. Then I also, could be the case, then I also don't receive anything. So many reasons, the result is always the same, I don't get it. After a while, A will repeat this. And now B sees, okay, there is a new packet, a packet with the number 1, because B can compare this. Look, before up there I had a packet with 0, and now I have 1. Okay, for B that means perfect, I can give this to the network layer, it's a new packet. Did the same up here, I also gave this packet number 0 to the network layer. Okay, and now I send back an acknowledgement, let's make it simple, also with the 1 here. So why is this important that we have the 0s and the 1s? Well, look at the next example. Now we send a new packet with yet another number, and we will learn that it is enough to reuse the single bit and now number this again with 0. If everything is fine with the packet, we pass it to the network layer. But now something happens. We lose the acknowledgement. Acknowledgement for 0. So what will happen after some time? There is no acknowledgement. And for A, the situation we have up here, we lose the packet, and this is why we don't get an acknowledgement. And the situation down here, we lose the acknowledgement, and this is why we don't get an acknowledgement, is basically the same. We don't get an acknowledgement. So how do we react? We resend the packet here with a 0. And now it's important for the receiver to detect, it's a duplicate. Why? Because also here we compare the number, which we call this a sequence number, and say, oh, it was 0 here, 0 there. That means that's the same packet. Then we think, oh, A is so stupid. It resends the same packet. Okay, we acknowledge again this packet. So this works with the M and M for arbitrary sequence numbers. But here in this case, we talk about alternating bit protocol. You can try this. It works with a single bit in this very simple setting. So you see, by using a 1-bit sequence number, just a 1-bit flag, we can detect duplicates. Again, the problem is A, as a sender, cannot distinguish between, frame dropped, so B never saw the frame, and the situation acknowledgement dropped, so B saw the frame, it's just the acknowledgement that got lost. A will always react with, okay, I have to resend the data. And thus we need a way, and this is the single bit, to distinguish duplicates from new packets. This is a very simple protocol. You can avoid buffer or receiver overflow, because if you do not acknowledge, then you are not allowed to send, etc. But there's always a long waiting between the transmission of blocks. You see, you send something and you have to wait for one round trip time, because if you go from A to B and back, that's one round trip time, as we learned. And this takes long. Additionally, what happens if we have very rarely the situation that we have an error? So typically it just flows. We still wait for the acknowledgement. Why not sending more and more and more data? Because the capacity is quite low. I mean, think what you send something, you have to wait. So most of the time you're only waiting. So you waste transmission capacity. And this all depends on the round trip time. So for long round trip times, this is not a good idea to use alternating bit protocol. But there are real systems using this, Bluetooth, for example. And there we don't have a long round trip time because Bluetooth systems, personal area networks, the devices are close by. So very short round trip times. Additionally, Bluetooth anyway works in a half duplex settings. You will learn more in mobile communications about the classical Bluetooth. So, you see, here we have a very basic setting with this alternating bit protocol, and you see also that we automatically trigger the repetition of sending a packet. So you repeat it automatically. Automatically, why? Because you have a timeout. If you do not receive acknowledgement within time, you repeat it again. You repeat the packet, no matter if the packet is lost or the acknowledgement. So it's automatically repeated. So that's a very basic principle. ARQ will see this many times. Okay, we can implement this, and it's a very, very simple protocol. And you see now that also the sender, if you compare the slides, the sender also waits for events. So the receiver waits until a packet comes in, and then you hand it over from layer 1 to layer 3. And additionally, you send your acknowledgement, and then you wait again. And the receiver side waits after sending until it gets the acknowledgement. And you see, you will not forward the acknowledgement to the higher layer. This is something layer 2 handles. This stays in layer 2. You get it from the physical layer and stays there. Then you can continue forwarding data from layer 3 to layer 1, and you wait again, etc. So that's a simple example how you can implement this very simple stop and wait. Okay, what happens if not only A sends data to B, but also B sends some data to A? So we want to send data in both directions. Plus, the channels may have errors. Okay, so both directions, full duplex, plus errors. So we have to extend this very simple approach. So naive again, why not using 2 times our simple communication channel with stop and wait? But this is really waste of resources. Acknowledgements are quite small compared to data. Why not using a single channel and we mix data frames and acknowledgements? So instead of having 2 systems, it's 1 system and we mix. Okay, this can be done, but now this means we introduce types of data packets. So with the simple solutions, you know exactly from A to B is always data, from B to A is always acknowledgement. So we could have this 2 times. That's not clever. So why not using types of data packets? So if you send something, you know it's either data or you know it's an acknowledgement, and you can distinguish it. Okay, but this means that there must be some indicator, for example, a number telling this is data or this is acknowledgement. So type of data packets. Okay, so we have to be able to distinguish. Plus, we can do something that's called piggybacking. So if we send data, so in the classic example, we send data from A to B. And now we send back an acknowledgement. But maybe B also has to send data, then why not piggyback the acknowledgement in this packet? So that's one of the ideas. So basically you could wait a bit. So you do not send immediately the acknowledgement back, but you wait a certain time, maybe until you also have data to send, and then you send back the acknowledgement. This is more efficient because, as we'll see with certain protocols, for example, if it's just some bits, you simply squeeze them into the header of the data packet and that's it. So you do not need an extra frame for it. Well, the question always is, how long do we wait? How long do we wait before sending back the acknowledgement? If we always have to send data in both directions, that's no problem at all. But what happens if A wants to send a lot of data to B and B maybe from time to time sends some data, then maybe this is too long. We cannot wait that long. So we can estimate the time, or well, best idea would be round trip time gives me roughly the time, the duration, how long I have to wait before I can expect an acknowledgement. So maybe I wait 2 times the round trip time, something like this. And if I get an acknowledgement within this time, either piggybacked with data or an explicit acknowledgement, then everything is fine. Okay, how does this look like? So you see, we extend our simple scenario. So that's the classical way, as I showed it. We have data in one direction, acknowledgement in the other direction. So that's the idea, and we do it data acknowledgement, data acknowledgement. So why not combine this? And this is now our piggybacking, that if we have anyway data to send, in this case from B to A, we can combine this and then send it over, and then again we can combine this, not in the beginning because there was nothing to acknowledge. That you see in the scenario on the right hand side here, data from network layer arrives. We cannot send it, we have to wait for the acknowledgement. It's here, and then we send the data together with the acknowledgement for this packet. So you see here you have the acknowledgement for data from A, you piggybacked it, and with the next piggyback packet you have the acknowledgement for the data coming from B. So that's quite a good idea. So piggybacking is a classical mechanism used not only in layer 2 but also on layer 4, for example. TCP is a typical protocol doing a lot of this piggybacking. So that's quite good. But still, we have this, well, we send the data packet and then this packet is acknowledged. So that the throughput is not too high, as you see from this. So why not sending more data? So not only one frame, but maybe several frames. Because right now we can only send one frame, wait for the acknowledgement, send the next frame, wait for the acknowledgement. Piggybacking improves a bit by this piggybacking procedure, but maybe I want to send 3, 4, 5 frames because the receiver can easily buffer this. So we have to improve throughput. So the simple stop and wait is not very efficient. Okay, so how can we do this? And this leads us to a whole class of flow control mechanisms called sliding window. So what is the goal? So if we want to send more than just one data, one frame. So assume now higher layers say, okay, send data, send data, send data, send data. With a classical setting, we can send a packet, get the acknowledgement, send the next one, get the acknowledgement. Takes a long time. Why not simply sending, 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 and then we get all the acknowledgements, if the receiver can actually consume all this. So the idea is that sender and receivers agree upon a transmission window. So a transmission window basically tells the sender, okay, I as a receiver can handle up to, let's say, 7 frames, because I know a frame size is this and that bytes, so I reserve certain buffer size, and I know without sending any acknowledgements, I can simply receive those 7 frames, can store them. So we agree upon a so-called transmission windows. Though, if W is the window size, the sender then may send up to W messages without any acknowledgements. That's the idea, to be a bit more efficient, and hopefully nothing happens. So that's the idea. So the receiver tells the sender in the end, okay, now I'm ready to receive a certain amount of frames. To be more efficient, as I said, we want to send several of these frames, not only a single one, like in the alternating bit protocol. We need not only a single bit, but real sequence numbers to identify the message. So a single bit is not enough because we want to send several frames. With a single bit, I cannot distinguish several frames. So we need sequence numbers, and we number the messages. So sequence numbers, quite often you may read also in the standard, it's written as SEQ or something like this, sequence number. And so you code it with a certain number of bits, to the power of n is the number of different sequence numbers. And what's quite important, sooner or later you will get a wraparound. Because you can imagine you start with a 0, 1, 2, 3, 4, 5, 6, 7, and that's it. If we only use 3 bits, for example, as a sequence number. Then we wrap around here and restart with 0. That's just an example. This has certain consequences. But for now, well, remember, we have a number, 3 bits, for example, and then we say, okay, this is packet 0, packet 1, packet 2, etc. The receiver now tells us acknowledge number 5, for example. Then it confirms the reception of the frame number 5. We can optimize this by telling, okay, I acknowledge all packets up to number 5 and including 5, for example. That's one of the ideas. And if there are some packets outside the window, then you discard it. What does it mean? If I, as a receiver, tell you I can now receive whatever unacknowledged 5 additional packets and you send more, well, I will discard them, otherwise I've got a buffer overflow. I cannot store it. So frames outside the windows, I will give you examples, are discarded. And then, as we always see, also will see, is that we slide the window of possibly unacknowledged packet as soon as an acknowledgement arrives. You will understand this looking at the example. And that was the core idea, that I buffer all the frames in a window, because it could be the case that they need retransmission. So if you have a certain window size, we need a buffer for W, in this case, also W frames. Okay, bit theoretical example. Then it's easier to understand. Okay, we have now a very simple example and this simple example has 3 bits for the sequence, or so acknowledgement numbers, so for numbering the packets. So with 8 different values, starting from 3 times 0, 3 times 1. Then we agree upon a certain window size, and this now depends on your buffer size. So for example, I could say the window size is 7. Here it has been noted the window size at least has to be 1, because otherwise I cannot send anything, so at least 1 message or 1 frame must be less, not less or equal, must be really less than the maximum sequence number. Maximum sequence number M, that was 8. So the maximum window size here is, the maximum value is 7. So we cannot have a window size of 8 or 9 or 10. 9 or 10 or larger, that's quite obvious, because then we have the wraparound. 8 doesn't work. Think of it why. We'll come back to this. So the window, and that's the idea, limits the number of unacknowledged frames. Well, it was the idea that we have to be a bit more efficient, higher throughput. So if the window size is 7, we can send 7 frames without any acknowledgements. That's the idea. So 7 frames, no acknowledgement, to be more efficient. And in an ideal case, then I'm not allowed to send anymore. In an ideal case, I will get back 1 acknowledgement with the right parameters, acknowledging all 1, 2, 3, 4, 5, 6, 7 frames. That's the idea. Shifting, I will explain with the help of these examples. So now a concrete scenario, and then I will come back to this, how I shift and how the numbering goes. We have here a setting for certain window, 0 up to 6, so the window size is 7, as indicated up here. So we have a window size of 7, and this is exactly here our 7. That's the window size. That's our window right now. Okay, now what happens if I now get a certain acknowledgement? This orange window with the acknowledgement 0, okay, that means perfect. The receiver tells me I've got frame number 0. If I got frame number 0, that means for me internally I can forget frame 0. On the sender side, I don't have to store it anymore, because the sender also has to store frames. Why? It could be the case that I do not get the acknowledgement 0. So it could be the case that before I don't get the 0 here, this would be an alternative because something went wrong, either with the frame 0 or the acknowledgement. Then I have to be able to retransmit this frame. This is why I cannot simply forget it, fire and forget. No, I have to store it until I really receive the acknowledgement. And after receiving, then I know, okay, the receiver on the other side got it. I can delete this in my memory, and I slide the window according to the acknowledged packets. And this is why it's called sliding window, because now the window still has the size 7, as you can see, but I slide it. What does it also say? Okay, as I slide the window, because the window tells me how many packets can be unacknowledged. And you see here, we have right now only 6. But the window says 7. So I can now also send here number 7. It's under the window. Perfect. I send now this 7. So packet number 7, for example. So what else? Now I receive, for example, Act 2. Act 2 means frame 1 and frame 2, the next one, they have been received without an arrow. That means for the sender, I can delete them in my memory. I don't have to repeat them because Act 2, that's the semantics here, will tell me everything is fine up to frame 2. Okay, so now I can send, and now don't get confused, I can send packet number 8 and packet number 9. So we start with packet 0 and so on, packet 8 and 9. So what does it mean? Well, packet 8 has now the sequence number 0 because we only have 3 bits for sequence numbers. We do not basically count the packets, but we reuse the sequence numbers. So we only, well, we have to save bits. So we cannot have millions as sequence numbers. So we have a wraparound, we calculate modulo 8, and here we reuse the 0 and we label packet 8 with a 0. Is this a problem? No, because we already acknowledged 0 long ago, deleted it from our memory on the sender side, the receiver acknowledged it and knows, okay, everything is now fine with this 0. So we don't need the sequence number anymore. So this is why we can reuse the 0 here for the 8th packet. Because we have the window slide a bit to the right, we can also send packet 9 and reuse here the sequence number 1. And now we can continue. So that's all history, all the old packets. And now, for example, the sender, and you see, you do not have to, and this also saves also again a bit of the data rate, we do not have to acknowledge 0 and 1 and 2 and 3 and 4 and 5 and now 6. No, in our example, it's okay. We acknowledged 0, we acknowledged 2, and this implicitly also acknowledges the 1, not only the 2. And if we now acknowledge X6, we implicitly also acknowledge 3, 4, 5, and 6. And this shifts our window quite a lot. So as you see, we shifted the window and we can now send new packets, 10, 11, 12, 13, etc. So you see, you let the window slide over all the sequence numbers. We reuse the sequence numbers, and by acknowledgement, we acknowledge all the frames up to this sequence number. So why is the window maximum 7 in this case and not 8? 9 or 10, that this is too large, I think this is quite obvious. But why is the window size really smaller than to the power of n with n bits? Well, in our example with the 3 bits, that gives us the 7, this sequence number 0 to 7, and we reuse them. Window size, now let's assume window size is 8, which is illegal, but now just let's assume it. Now A sends 3 frames to B, just 3 frames, and B acknowledges frame 2 with Act 2. So Act 2, sending to A. And B has now acknowledged 0, 1, and 2. Let's assume we just started. So we sent 3 frames, frame 0, frame 1, frame 2, and we sent act 2. Perfect. Well, everything is nice. So we now, from the outside world, we know everything is acknowledged. Now, A sends 8 frames without an acknowledgement from B. So 8 sends the additional frames 3, 4 with the sequence numbers 3, 4, 5, 6, 7, wrap around 0, 1, 2. This is 8 frames. 8 frames. So, what happens? Now, it could be the case if A now receives acknowledgement act 2. It could be the case that so far B has only received 0, 1, 2. That means it could be the case in communication protocols that, okay, well, I didn't receive anything, I repeat. Many protocols have this, I repeat my last acknowledgement because maybe it's lost and there's no reaction from the other side, so I repeat act 2. This could be the case. Okay, but this could mean now that I only got 0, 1, 2, but it could also be that I received all these new 8 packets, 3, 4, 5, 6, and so on, and I mean I acknowledge this 2. So either this first 2 or this second 2. The problem is, if you allow the window size to have the same size as 2 to the power of n, with n the number of bits with a sequence number. So then we run exactly into this ambiguity. So A doesn't know now, is it case 1 or case 2? But if we restrict the window size being really smaller than 2 to the power of n, so 7 in our case maximum, then this cannot happen. Try this on your own, you will see this situation cannot show up if we follow this rule that the window size always has to be smaller than 2 to the power of n with n the number of bits, 7 in our case. So maximum window size 7. You can have smaller window sizes, but not larger window sizes. Okay, now we know, okay, we can number with a certain window size. The window size reflects the capability of the receiver to receive a certain amount of data frames without any acknowledgements. So the receiver can still control when it acknowledges and how basically to regulate, to control the data flow. So we have some more issues when it comes to the round trip time. Sliding window sounds good, but how does this play together with the round trip time? We learned now that we can send several frames without being acknowledged, but we also know that it takes a while before we get back the acknowledgement. So, and this time here, that's our round trip time. This can be quite high. So, for example, for classical mobile phone systems, packet traffic, this could be half a second, which is quite long. Or think of satellite systems, you have 200 milliseconds, 400 milliseconds, depending on what type of satellite. So this could be quite high. So long round trip times affect the efficiency. Because if the window size is small, you see, we have a long time where nothing is going on. So maybe you have more data to send and maybe there was no error at all, but you have to wait for the acknowledgement and then you're allowed to send data. So this is inefficient, this waiting time. That's very, very, very inefficient. So if we have, for example, our slow satellite or old classical packet-oriented cell phone, high delays, so it needs a certain time for the frame to process and to send, certain number of sequence numbers, a window. Then you see this example. We send our 4 frames and we have to wait. But the sender is blocked most of the time. 96% if you do the math here. So the utilization of the channel is only 4%. And this has nothing to do, or not that much to do, with the data rate. The problem is the round trip time. And overall we can say, if bandwidth times the delay is large, you need a big window to really fill what we call the pipe. So we pipeline our data, we send it into the pipe, and what we try to do is to keep the pipe full all the time. So if we want to transmit something, we try to keep the pipe full. So what we need in this case is a much larger window so that we can really use this pipe. You can do the same math for, let's say, if we have a 100 gigabit per second link and the delay is not that high, but maybe it's a transatlantic connection where we don't even have to go there, but think of a 10 millisecond delay. So just do the simple math. How many bits you can store? That's also kind of storage capacity of the line. 10 milliseconds, 100 gigabit per second. You see, whoa, that's quite a lot. Many megabytes you store there. And now depending on the size of the frame and bytes, etc., the windows should be very large. So if you have high data rates, long round trip delays, then we need large windows. Why? Because we want to be able to fill the pipe. But what is the problem? What happens about, well, flooding the receiver? Or what happens in case of bit errors, packet loss? If you have a big window size, that means you can send a lot of data without any acknowledgement. So, and that might be a problem. Or you can send a lot of data before the receiver can even react and tell you, oh, maybe the window size is too big. We'll come back to this issue, talking about TCP and higher layers. So, large windows will allow you to really use the medium, send a lot of data, but we cannot really control the flow anymore because it's a large window. So there's a lot of data arriving on the receiver side. So we have to take care. So there are different trade-offs we can make with window size depending on the data rate of the medium, the round trip times, etc. So what else can we do and how to handle this pipelining? Well, there are different ways of handling it. One classical scheme is the so-called go back n scheme. Here, if we have a go back n, what does the sender do? The sender transmits frames and has to buffer the frames according to the window size. That was exactly the thing that I said, okay, as long as the frames are not acknowledged, we have to store them on sender side because it might be the case that we have to retransmit it. Additionally, after sending a frame, you start a timer. So each frame has a timer. So this is why we need these efficient timer structures. we quickly touched. So that's one of the ideas. We need a timer, because we expect to get an acknowledgement after a certain time. So what is a good expected time? Example, maybe 1.5 times round trip time. Only round trip time, well, maybe you also need some compute time, etc. But maybe 1.5 times the round trip time is a good idea. So you shouldn't wait too long. So you have to retransmit, but well, don't be too nervous. That's also not a good idea. So that's just an example, or 2 times round trip time, something like this. So as soon as you get an egg, that's nice. According to the window, you can send new packets, as I just showed you with the example, but you also update the buffer. That means as your window slides, you can free the buffer, so you can remove the acknowledged packets from your buffer. That's good. And now we have a go back and scheme. That's a simple scheme. We can say as soon as the timer expires for a frame, we retransmit all buffered frames. I will show you this with an example. So this is this go back and. So basically you say, okay, I don't get for a certain acknowledgement for frame 5, and I've also buffered some others, so I resend everything. So that's the idea. We go back and retransmit everything. The receiver does it in a simple way, so all the correct frames are acknowledged and incorrect frames are discarded, and you do not send an acknowledgement. So very simple for the receiver. We don't do anything, we don't send acknowledgement if something is incorrect. We could also do otherwise, but that's this example. So how does it look like? Now look in this example, so it's now rotated by 90 degrees. We have our source, that was our node A in the examples before, and we have the destination. And now we send our first frame. You see, it arrives here. But as we have a window, we also send frame 1, frame 2. So, okay. And the receiver sends back the acknowledgement for frame 0. And in this example, as soon as this arrives, we can send our packet 3. We send the acknowledgement for 1. We send the here acknowledgement. We send here 4. And depending on the window, we can even send more. Okay, maybe the window is large. That's not the point. But as you see here, we may lose a packet in between. So this could be the case. It's fully okay to send 3, 4, 5 because this depends on the window. We send, as we learned, several packets within the window. They can be sent unacknowledged. But now it happens that we lose somewhere our packet 2. It never arrives. And then, yes, we get packet 3. Okay, that's strange at least. We get packet 4. That's also strange. And packet 5. But okay, the receiver is still missing. And now it depends on the implementation what you do. In our simple case, no egg is sent. So the receiver is very simple and doesn't do anything. Just maybe thinks, okay, maybe there's something missing, but I don't do anything. But on the sender side, we have a timeout. And the simple scheme go back and then says, okay, we have a timeout. We repeat all the packets we have in our buffer. What do we have in the buffer? we've got the acknowledgement for 1. So we dropped already 1 and also 0, but we never saw an acknowledgement for 2. So 2 is in the buffer, also 3, 4, 5. So we repeat sending everything starting from 2. And then we get the acknowledgement for 2, we can shift the window, for 3 we can shift the window. That's very simple for the receiver side, because the receiver side doesn't do anything, just doesn't send back the acknowledgement and ignores if packets arrive with higher sequence numbers. So as you see, we don't send anything. And the receiver, the sender is also quite simple. Well, after timeout, I go back to the very first packet that was not acknowledged, in this case 2, and then I start sending everything again. Why do I show this? This scheme is not very intelligent. Well, it's simple. And that's one of the starting points. If you have simple software, simple hardware, whatever, you can implement this. So this is not complicated. You don't have a complicated buffer management on the receiver side, because it's quite obvious. Why do we have to retransmit 3, 4, 5 again? 3, 4, 5. That's waste of data rate. I mean, we transmitted them already and they have been received, but not 2. And for the simple scheme, this means we have to repeat everything. It's quite obvious that we say, why don't we simply transmit the 2? Because we have already the others. The answer is, if you have a very, very simple hardware, well, then you cannot perform this, oh, I receive it out of order, I have to resort. No, this is a very simple implementation where we have this kind of FIFO behavior. I just say, okay, everything has to be received completely in order, and then I deliver it to the higher layer. Not very clever. So maybe the receiver should do a bit more, because here you see the receiver is a very simple one. I only acknowledge correct frames and I do nothing else. Okay, can we do more? So yeah, when we receive correct, then we send the acknowledgement. That's what we've done for go back N as well. But maybe we do a bit more. So when a frame is missing, at least, and this is now new, we buffer the following correct frames. With go back N, we said, well, 2 was missing. I don't care about 3, 4, 5. I simply don't care. I don't even buffer them because 2 is missing. But now we say, okay, the example before, it was this 3, 4, 5. Then maybe let's buffer them. Because we hope that maybe sooner or later, because we do not send an ACK back, then the missing frame will arrive. And then I squeeze it in and say, 2 is here. And I can now forward everything to the higher layers. And the sender uses our sliding window protocol. And in a very simple scheme, if you have an acknowledgement timeout, then you can repeat like go back N. But as soon as you receive the ACK, then you stop repeating. So it's still not perfect, but at least a bit better. As you see, we are a bit more efficient, but now the receiver needs a bit more buffer. That's quite obvious. So we started with a very simple go back N. The receiver doesn't need a buffer for the frames. It's just, okay, they come in order and we give it to the higher layer. Something is missing. We drop all the next frames until we get the missing one. Here, now, we buffer the frames, and as soon as the missing one arrives, then we can forward them in order to the higher layer. Great. Still, the sender does maybe something a bit stupid, but that's still simple. well, there's no acknowledgement. Then I behave like go back and repeat sending. Oh, now the acknowledgement comes. I stop repeating it. So it's a bit better, but plus you need a buffer. Still not perfect. We can do better. So this then selective reject. What we do is, again, we buffer the frames. So we have a missing frame. In our example, it was frame 2, but we buffer everything that comes after them. But what we can do now is we can immediately tell the sender, hey, wait, you're sending new frames, which is okay inside the window, but there's something missing. So I immediately tell this frame J is missing. So we could send a kind of a negative acknowledgement. So in our case, I could say, well, if I count the right way, 0, 1, 2 should be the next one. But you sent me 3, 4, 5. Hey, I'm still waiting for 2. That's one way of doing it. And then the sender says, okay, I've sent 2 already, but obviously it didn't reach the receiver. I also sent 3, 4, 5, but maybe I repeat only this one. And this is then very efficient. You have to repeat the missing one, yes, but you don't have to repeat frames that already have been received. That's the idea. We could do more. We can send, for example, a whole list of missing frames. So instead of a single negative acknowledgement. So we could say, okay, you sent now many, but I'm missing 2, 7, 14, and 37, for example, if I have a large window. Just an example. Oh, there are protocols with window size 128 or whatever. So this helps then the sender to repeat only those frames. But this means that I have to manage the buffer. So I have to do more complicated buffer operations compared to the simple go back n. Big advantage, we do not send duplicates. So it's very efficient. But it needs a bit more buffer, so it's a bit more complex. Okay, I know those schemes maybe begin a bit confusing, but if you compare the examples, this will be clearer. So, go back n, very simple scheme. First of all, go back n. Once again, what does it mean? We send first frame number 1. Everything is perfectly received, frame number 1, and delivered to the higher layer. Plus, in the simple scheme, we send the acknowledgement, arrives on the other side. Perfect. That means here, for the sender, this very first packet can be dropped from the memory. Then we send number 2. In this case, 2 is dropped. Sender doesn't know it. Well, receiver notices it that, okay, there's no 2, but I see a 3. Oops, there's something missing. The simple go back n, it simply says, I don't care, I want 2 first. I got 4, I don't care, I want 2 first. I got 5, I don't care, I want 2 first. I got 6, I don't care, and so on, and so on. And you see, well, it receives all these frames, but as this is a very simple device, it cannot do anything with this. 9, I don't care. Meanwhile, on the sender side, we have a clock ticking after sending 2. Same is true for 1. It waits, and then the sender says, okay, I waited too long, I will repeat 2 because I never got an acknowledgement for 2. Then, and this is exactly now the go back n, you start again with 2, 3, 4, 5, etc. And then you receive in order your packets. And then, perfect, you can send back acknowledgement for 2, acknowledgement for 3, and so on for 4, 5, and so on, and so on, and so on. And now you see now we receive everything in order, etc. But you also see we waste a lot of our data rate because we repeat, which is not necessary, 3 to 9. 3 to 9, we sent this already. So this is not a good idea. It wastes data rate because, well, you repeat and repeat things you already sent, successfully received. But it makes the receiver very simple because the receiver just waits, I want to receive everything in order, otherwise I don't do anything, I drop. So very, very, very simple devices. If you can do a bit more, we have this selective repeat. What does it mean? Same scenario, we deliver the first one, that's perfect, we acknowledge it, we lose number 2, but now we do not drop, but buffer those frames 3 to 9. We buffer them, so we do not drop them. Again, we have a timeout. We repeat the 2. And now what happens? Well, layer 2 on the receiver side waits until it gets the 2, then it delivers 2 to the higher layer. But, and now this is the difference, immediately acknowledges up to 9. And this tells the sender, oh, okay, the receiver already got everything up to 9, and it will stop repeating. And you see in this case, we only repeated 3 to 7, which is also still a problem, but not as worse as repeating 3 to 9. And on the receiver side, we can now deliver after 2, we will deliver 3 and 4 and 5 and 6 and 7 and 8 and 9 to the higher layer. So after receiving 2, we can deliver 3, 4, 5 and so on up to 9 to the higher layer. And then we receive 3, we drop it, 4, drop it, 5, drop it, 6, drop it, and then 7, we drop it, and after getting 10, then should be here, after getting 10, we send the acknowledgement for 10, and then for 11, and for 12. So that is the idea. So it saves a bit, but not too much. And you need this buffering. If we now introduce additionally a negative acknowledgement, we are here at selective repeat, reject. Not repeat, but reject. What does this mean? So again, we send 1, 1 is delivered. We have a problem with 2. We send an acknowledgement for 1. Okay, that's fine. That's always the same for all 3 settings. Now we receive 3. 2 is missing. Again, we start buffering. We buffer 3. Okay, buffer 4. Okay, buffer 5. But what we also do is, as soon as we receive 3, we notice on the receiver side it should be 2. And we immediately send back a negative acknowledgement. So that now the sender a bit earlier recognizes, oops, something went wrong with 2 and repeats 2. You see, for go back and selective repeat, we have to wait for a timeout. In the case of selective reject, we do not have to wait for a timeout, but in this case we are faster. There should be an acknowledgement, we send it back, so we can now repeat 2, and then we send back the acknowledgements, etc., etc. But you see, also we send back ACK9 and so on. You see, we have to buffer less. We only, in this case, have to buffer 6 frames, not 7 frames. And we are a bit faster. We can immediately, a bit faster compared to waiting for a timeout. You see, we're a bit faster. We notice earlier that something went wrong here with this negative acknowledgement. So this is more efficient. Again, we have to buffer, plus we need a negative acknowledgement, so an additional data type. Okay, so you see, we can solve this issue of having errors and using sliding window protocol in different ways. Go back N, the simplest one, selective reject, and you can extend this to sending back complete lists of negative acknowledgements with several frames to be even more efficient. So different ways. There's a slight warning. We now mixed two concepts. So one is the error correction via ARQ. What was ARQ? In our case where you see, for example, here in this case of selective repeat, if we look at this, we see the ARQ, so this automated repeat request, automated. Why? Because there is a timeout. So it's automatically a timeout that tells us, oh, we have to repeat something. So this is automated plus, so automatically with a timeout, or automatically, and that's the other example, with our negative acknowledgement. So we request the repetition of data. At the same time, we use a sliding window protocol. Sliding window for flow control. We mix the two concepts, error correction and flow control, and we will come back to this mixing of these concepts, because there are certain consequences. You can do another way, but here you see how we have this sliding for getting packets that are acknowledged and sending only packets within the window. We mix this with ways of how we correct the errors. We'll come back to this. So sliding window, these are different versions how we can handle errors. Because otherwise it's quite simple sliding windows, but in real life we always have errors. Quick remark, as I mentioned, on timers. So we have many timers. Well, remember, we start a timer for each frame we send, for each frame. So many protocols require a lot of timers, but the computer doesn't have that many hardware timers. So we implement them with software, and typically using a linked list, and we update then the linked list depending on the real time. And so we say, okay, how many ticks, just for example seconds or 10 milliseconds or whatever we have to go, and as soon as we spend the time here, then we delete this element, and then we simply point to the next element, and so on. And as soon as we need a new element, we simply append it to this very simple linked list. So that's one way of implementing timers. So we don't have to start a real timer for each frame we send. Okay, that's quite a lot, but flow control is important already on layer 2, where it's still relatively simple. We'll come back to flow control again on layer 4 and why we have it and how it influences overall the stability of the whole internet. Here, again, we are on link layer. Link layer, that is between your computer and a switch, for example. So point to point or point to multi-point, typically local or point to point. There could be transatlantic links, but it's not that complicated setting. So we don't talk about applications, etc. That's very basic flow control. But why do we need this at all, this flow control? Looks complicated, but why do we have it? Then we talked about windows and window sizes. So what determines the ideal window size? What is the ideal window size, and what are the parameters influencing this window size? please do go through this example for the max window size again and understand why really this window size has to be really less than 2 to the power of n. Play a bit with window size equals 2 to the power of n, and then you will see what the problem is. Then I briefly touched this mixing the two mechanisms, flow control and error correction. Why could this be a problem? So flow control, controlling the flow of data within the window, and the other one is error correction. So what could be a problem? Think of the motivation for flow control and the sources of errors or missing acknowledgement or not acknowledging data. A bit more complicated. Alternating bit protocol, that was a very simple protocol, low efficiency, but as I told you, it's used, for example, in Bluetooth. Why is this the right choice there? And not a good choice if you have a intercontinental link and you want to do the flow control there.